This is lecture 11, the continuation of section 4.2 in chapter 4. This is a follow on to lecture 10. In essence, I could have combined lecture 10 and 11 together, but I opted to separate the two. In this lecture, I'm just going to be going over two final examples in 2 dimensions, just so that you're comfortable with the concept and make sure that you understand it. And then in lecture 12, we'll go to 3 dimensions. So this one example, this is on the example 11 worksheet that I posted on Canvas. And in this case, we're asked to find the reactions at D, C, and B. Now, when we first look at this, it's a fairly simple structure, but it's good to identify right away what's what. So DC is a 2-force member, if you haven't guessed already. It's connected at D, it's connected at C. So when we're asked to find the reaction at D and C, we know that the magnitude of those are going to be exactly the same because the force is connected between D and C. So that lets us know at C where the force is going. It's essentially going up to the right at a 45-degree angle, and we know that because of the quarter circle. So with this, as with the previous problem, we can solve it using a force triangle, or we can solve it using a standard summing the moments. Oh, and by the way, B is equal to, sorry, I didn't put B in there. B is equal to 60 millimeters. So missed that. So B equals 60 millimeters over here. That will be important. So if you wish at this point to try it on your own, go ahead. I would suggest you could try it doing force triangle, or you can try it out using just summing the moments and picking which point you're going to look at. All right. Okay. So if you opted to just go ahead and do it on your own, I'm first going to show you quickly the force triangle method. And in this example, I've first drawn a sketch of the diagram. So 60 millimeters, 90 millimeters, 160. Recall that this whole distance here was 250, and we know that's 90, therefore this part from C over is 160. Now, the force triangle method, I'm just going to go ahead and show you, is if we go ahead and we were to draw a line through DC, we know that that line is going to be at 45 degrees because that's a quarter circle. We also know that we can extend the 80 Newton up and down as far as we want. So if we extend the 80 Newtons up and we draw the 45 degrees of DC, or we'll just call it C, maybe it's easier just to label it that, then we know that the reaction at B has to go through that common point. So now we can figure out what that is because we know where it's going to go. Now, because this is 45 degrees, we know that this is a right triangle. So we know the distance from here to here has to be 160, just like it is down there. So from that, we can actually use the distances to go ahead and calculate the angles. So for example, this angle here, which I'm referring to as omega, is simply equal to the opposite side, which we now know to be 220 millimeters, over the adjacent side, which is 250. That gives me an angle of 41.35 degrees. Now, so if I were to draw this up here, I know that that has to be omega also. So if we go a little farther and we look at our force triangle, the way we've drawn it, we have the 80 Newton force down. We know we have the 45 going up this way, that's our D or our C, and then we know that B is coming back. Now because we know this omega from previous, and we know this is 45, we know that these must add to 90 degrees, so the difference in the middle ends up being 3.65 degrees. So this little 3.65 degrees is opposite the 80 Newtons. So that's where we get our first number for our law of sines. Then we know that opposite B is the 45 degrees. So there we have that. And opposite D is simply 90 plus the original 41.35. All right. So that was a pretty easy geometrically to figure out, and you have your answer. Okay. Now let's say that you don't like the force triangle and you want to look at it in the conventional method. There's nothing wrong with that. You go ahead and look at it. We have, if we draw, we have something that looks effectively like this. So here's B. I'm going to draw the reaction. So we have Bx, we have By, we have 80 newtons, and we have this, I'm just going to label it C. Again, C and D are the same. Now, I've drawn this here to kind of show you how the forces are going to react. We know that if C is going up that way, then that means that this actual quarter circle is going to have a force that's equal and opposite to it. And then on the other end, it's going to have a force opposite to it, and then D is going to be going that way. The reason we have to do that is that this, if both forces on this quarter circle were in the same direction, then it wouldn't be in equilibrium. And also, when we take this and place it back on top of C, you have to have these forces effectively cancel because it's in equilibrium internally. This will become a very important concept when we get to chapter 6, when we start talking about frames and machines. Even trusses, to a certain degree, are going to do that. So now that we understand that, let's go ahead and look at the problem. So we've seen how C is affected. So now C, I've drawn this from what I think it looks like, but I don't know that for a fact. C could be going down and to the right, possibly. But then we have to think about it, is that going to be a balanced force system in this bracket here? So we're going to go ahead and use our three fundamental equations. We know that we're going to sum the forces in the X, sum the forces in the Y, and sum the moments. And so with that, we can then think, what do we want to do first? So in this case, I'm going to say, let's sum the moments. And as before, we sum the moments about the point B, because that gets rid of two of our unknowns that we don't want, or we want to find. And that allows us to just solve for this force at C. So sum the moment at B to 0. And so what do we have? Well, we know we have around B, we have 80 newtons, and that's times 250 millimeters, or 0.25 meters. And that's a positive moment because it's counterclockwise. And then we have plus C cosine 45. And so in this case, I'm breaking C into its respective components. We have one going this way, and we have the other going that way. So C cosine 45. So this here has a distance of 60, or 0.06. And that's also positive because that's going to want to make it go counterclockwise. And then we have the other part. And since we know that the C is equally vertical as horizontal, then really we're looking at which one's going to have the longer moment arm. Well, the one that's going this direction is going to have the longer moment arm. So it makes sense that this would be going away from that, because if it was going down and to the right, then this would be negative, but the other term would be positive, and we get a net negative number. So we guessed correctly in this. So lastly, we're going to say minus C cosine 45 degrees times 0.09. All right, and all that equals 0. So meters. So we go ahead and solve, and we get C is equal to 943 newtons. All right. Then it's just a question of summing forces. So if we sum the force in the X, 0, we know that the way I've written it, I have Bx minus C cosine 45 degrees equals 0. So therefore bx equals 667. If I do the same thing with by, summing my forces in the y direction, I have by, and that's going to be, sorry, by. Now I've written by to be positive, so I'll just leave it that. So by plus 943 newtons. So I have byf. So I have not plus 943 newtons cosine 45 degrees, and that's minus 80 equals 0. So I can see that's a much bigger number than that. So I'm going to get by equals a negative 587 newtons. And so by equals 587 newtons going down. Now, if I find b, the magnitude, that's just going to be 667 squared plus 587 squared square root, which is going to give me roughly 888. All right, so 888 will be partially more equal than 666. And so when we come back up to here, after the fourth triangle, then it turned out that b was 888 and at an angle 41.3 because we knew that b was going down this way. And we knew that d was 943 going up that way. And so we got 943 here, same thing. All right. So that's a comparison between the two methods. You have the force triangle method, where you find that, and this could have been a mirror. You could have flipped it over. You could have had it look, it could have looked just the opposite, in the sense as it would have been something more like this, and then down, and then back up. We could have had something like that too. Would have been, still would have solved it the same, wouldn't have mattered. All right. So hopefully that's clear. And I have just one more example I want to show you, and that'll be that till we get to dimensions. Share the screen to show you that problem. So here we have this ramp, 250 kilograms. It has a center of mass. Okay, here we are. Sorry, you probably heard the phone ring. I had to pause for a second. Life goes on even when you're lecturing. So this one, how we have the ramp, and we have a force at C. We have the we have a pin at C. And remember when we talked about pins, how the only reaction has to be normal to the pin, meaning that this pin is going to be pushing normal to the ramp. And then we have the tension on chord AB, and we have the free roller at A. So it's only going to have a vertical. So this one's another problem that's actually not super challenging. As you found with these 2Ds, that they're kind of a recipe. They are a recipe. Each one, essentially, you have your three basic equations of equilibrium. You sum the moment about the point with the most unknowns, and you're done. So let's look at this one. So here we have it. So we have the 250 kilogram ramp. So that's going to be at W, our center of gravity. That's going to be at halfway up the ramp. We have our 0.5, 0.2, 0.3, and then C, as I said, is a normal to that. And then we have our reaction at A, which is just a vertical because of the rollers. So we have three unknowns, so we can't just sum the forces away. But notice how the tension AB goes right through the point A. So because of that, if we sum the moment about that point there, which we'll call A, then that effectively eliminates this tension in that, and we can solve for C. So let's go ahead and do that. So if we sum our moment dot A to 0, we know that we have C. Now, C is the way I have it drawn. I think C is pushing up, and so the reason it's pushing up is because the pin, the weight of this is pushing down on the pin, and the pin is pushing back up on it. So it's kind of like if something's resting on the ground on a lever, the lever's pushing up, and the lever's pushing up, and the plank is pushing down. So same thing here. So C goes that way, W goes that way. So if we do that, we get C times 0.7 meters minus 250 kilograms times gravity. And you could do this beforehand if you want to not include it in the calculation. And then that's going to be multiplied by the distance, which is 0.5 meters times the cosine of 30 degrees. Okay, so we get, and all of that equals 0. Sorry, got to plan ahead when I write those. So we have C times 0.7 meters, this distance, creating a counterclockwise moment, minus the weight, 9.81 times 250 kilograms here, and the distance, if we were to project that down, is from here to here, which is just simply 0.5 cosine 30, and all that equals 0. So C gives me a value of 1,517 newtons. So now if we want to find the others, we'll say sum the forces in the x to 0. And in that case, because A is completely vertical, we know that the tension AB times cosine 15 degrees minus C sine 30 degrees. And so where did I get that? I know that if this is pointing up, I know that effectively this force can be broken into a force going like this and a force going like that, where this angle here has to be 30 degrees. So it's this little component, C sine 30, that's giving me this. And that equals 0. So my tension AB gives me a value of 785 newtons. Then I do the same thing, sum the force in the Y, and I get, and notice how in the tension AB also has a Y component. So if I had summed the force in the Y first, I would have had two unknowns I couldn't solve. So you may see this and pick the one that you can solve for first, but either way, it doesn't matter, because once I wrote it out, I'd still have to write once I wrote it out, I'd see that, and I'd still have to write out this equation regardless. So sine 15 degrees, tension AB times sine 15 degrees plus A minus 250 times 9.8, and then plus C cosine 30 equals 0. So we have our tension AB, sine 15. So that's this part going up, plus A going up, minus 250, plus the C cosine 30, which was just, again, this side of the triangle. And we end up with A equal to 936 newtons. And that's it. And A couldn't be negative, and so if it was, A can't be a downward force, because if we have a set of rollers, as you can imagine, it can only push up. The rollers, if the force was net that way, then the roller would float off into space. Okay, so that's that. That's the end of this section of 2D. And so what we'll do next time is 3 dimensions, 3D, and we'll find that it's essentially a very similar way of approaching the problems, just a little more vector math, but otherwise pretty doable. And once we're done with that, we'll be through everything we need for the midterm, and we can look forward to that. All right, thank you, and I'll see you in the next lecture.